So, hello, Mara. How are you doing?
Fine.
It's been an interesting 2 weeks since the 1X reveal of Neo, and we've been able to do, let's say, a little bit of investigating since then, and get kind of an understanding of what's going on. So, if we just kind of back up about 2 weeks ago, 1X announced their new robot, the Neo, which is the next generation after the Eve bot, and it looks an awful lot like a real humanoid, as opposed to the first one, which was sort of humanoid-esque, didn't have real hands, didn't have real legs, was using wheels to go around. This one was so good that everyone thought it was a guy in a suit. Okay, so which is considered one of the biggest compliments out there. And since then, there was several interviews with Bernd and some other members of the 1X team about, you know, how the development is going, how they're doing different things. There was the spaces that both you and I were in, along with Bernd, where we get to ask a couple of interesting questions. And so we've been trying to, let's say, peel a couple of layers off the bot because we know the bot is wearing a tracksuit, which is there not just for protection, but seems to hide a lot of intellectual property that's going on there. And with most of the other humanoids, we know they have actuators, which are usually at the joints around their little motors to make the things move around. And we know 1X is doing it a little bit differently in that they're using these tendon drives, but still, it's not like they're just using tendons to move things. They're using it as part of the actuation system. There's got to be some motors in there somewhere. And they've done a couple other revolutionary things. So, do you remember, how much does the Neo weigh? Do you remember?
Yeah, it was 35 kilogram.
Yeah, was it 35 or 30
I
kilograms?
think
I
I
think it was
think
around,
30 maybe 30 or 35.
yeah, 30,
Yeah,
which is absolutely remarkable because Optimus, for example, we don't know the actual weight. We know that they've stated it's 125 pounds, which is about 55 kilograms. I did some kind of back of the envelope. I made a spreadsheet where I did the bill of materials, looked at where Tesla had actually said what the weight of all the different actuators are, counted up all different actuators, figured out how many batteries in there, how much all the other stuff would be. And I was able to get kind of close to that, somewhere around 55, 56 kilograms. So how do you get from 56 kilograms down to 30? It's like, wow. I mean, that's gotta, how do you get to there? And I think one key insight there is one is that we know from the discussion we had with Barrett is their battery pack is much smaller. And it's smaller because it is so efficient and that it's still able to get reasonable runtime out of the bot. But the battery pack is about 1/5 the size of the Optimus. So that means you're going from like 10 kilograms down to 2 kilograms. So I was like, okay, so that's 8 kilograms. We still got a long ways to go here. But I found if I went into my spreadsheet and divided the masses of all of the Optimus actuators in half, I came out around 32 kilograms for Optimus that way. So it's like, aha, what they've done is they figured out how to make their actuators much lighter than what you're seeing in the Optimus spot and basically in all the
I
others.
think now it's 30 kilogram. 30.
Yeah, yeah, yeah. So the whole, the interesting thing about it is, okay, they've saved a lot of mass there, and we know because Bernd has told us a lot of the reasons why they developed the actuators here. One is that they're looking for safety, and safety means you have to have backdrive ability, which means that if the robot hits you, that rather than it continue to go through you, you're able to kind of push it back and not get pinned by it. And that usually means you have to have a really low gear ratio. If you have these higher gear ratios, which most bots have, which are like the order of 1 to 100, they're not backdrivable. And transmissions and everything require mass and everything else. And so they said, well, we want to get away of that. So if you can get rid of the transmission system and all the gearing in there, then you may be able to make your actuator not only be backdrivable, but a lot lighter. So they've thrown that out, and they've had to come up with a design of having a high torque, low gear ratio, direct drive system, which we actually been able to find a little bit about on how they've been able to do it, because in 2020 they filed for a patent. I actually think earlier than that, I think it was granted it in 2020. There's a patent describing a little bit about what's going on. So now we can get an idea of what's going on and exactly what are the tricks of the trade that they're doing to reduce the mass and what is going on with these different tendons. So you ready to take a look at a
Yeah, you,
patent?
you, you already have been doing all of investigation. So I think that's really fascinating. So please go and share.
Yeah. Now, everything we're doing here is based on public statements and publicly available information that 1X has put out there. And once the patent's out there, it's public. And it was actually very easy to find. It was really easy for me because I've got a good friend. His name is Seti Park, that a lot of people may know on X, who just loves looking for patents and describing them and finding some of the key patents of of many different companies, definitely Tesla, but just looking at a lot of the others. And I just said, hey, have you seen any from 1X? And like within 30 minutes, he was able to find one. It's like, okay, and this is very interesting. Now, just because he found it in 30 minutes did not mean it took me 30 minutes to read it. I had to read it like 3 or 4 times. And I'm still not quite sure I understand all of it. So what I'm going to do is I'm going to share the screen right now, and we can get a little bit of a look at this patent here. And okay, and we just froze here. So let's see what's going on when I did that. Okay, it takes a second for that to come up. And what we want to do is I want to do this entire screen here. That'll be a little bit easier. And then I'm just going to pop this up right now. Okay, so here we have the patent description, and it actually details quite a lot of different things. A lot of times the abstracts are kind of misleading. You get like one idea of what's going on, and then it turns out there's like even more description in there than just the abstract. So the first thing they do is they sort of show an outline of what a human bot would look like, and get into a description of a lot of figures of looking at the actuators. So they really go in and do a description of what they mean by a direct drive actuator. And direct drive, you would think, means there's no gears in there. They're talking about anyone that has a gear ratio below 1 to 10. And I believe their gear ratios are much less than that. That might be like 1 to 2 or 1 to 3 or something like that. And so it's like, well, that means you've got some sort of transmission or gearing in there. It's like, there's other ways to get a quote gear ratio that doesn't require gears that I think we're going to see in a minute. But the main thing is they're trying to come up with a high torque actuator, which is using both a rotor and stator where they have permanent magnets in there, and trying to figure out what's the best way to configure this thing to make it as efficient as possible. So they go into a big description of how you have to set up the magnets and everything, and what the thickness of the magnets have to be to make sure you don't get demagnetization, because if the motor runs too hot, then your permanent magnets may lose magnetization, demagnetize on you, and then it doesn't work anymore. So you've got to have all these different controls to make sure the thickness is enough that things like this don't happen. But one of the tricks that they've done is they're using for their stator something that's called a Hallback array. And the Hallback array is basically, if you take a bunch of small permanent magnets and kind of stack them all together, you can create a much bigger magnetic field, right? And the thing is, the magnetic field is going to be on both sides of that strip that you have. So basically, you're aligning north to south, north to south, north to south, all the way along there. And what that means is that a lot of the magnetic field is on one side where you don't really need it. You'd like to get it all on the other side. And it turns out if you take those permanent magnets and rotate them like 45 degrees when you stick them together, so it's not necessarily north to south pole, but it's off a little bit, and you do that, you end up creating a stronger magnetic field on one side of the plane than the other, which is rather interesting. So that's the idea of a Hallback array. Now, another problem they have to worry about is that most of these high gear ratio motors, the way they get their torque is they have a motor that's spinning at a very high RPM and then goes through this differential, of 1 to 100 to be able to get the really high torque. And because of that, the magnetic field looks very smooth to the spinning motor. But when you have a motor that's spinning really slowly, the magnetic field is kind of lumpy. It's not actually perfect all the way around. It's kind of a sinusoidal wave. And if you look at it, it almost looks like a gear. and so you get these two different magnetic fields that are trying to push against each other. And it's not pushing smoothly. There's a little bit of like this. And as you get moving a particular way, it'll pick up. But it's not a smooth torque that's going on there. And this is an effect they call cogging. So it's almost like thinking of gears and cogs in a wheel that things are going to stick in there. So they have different ways of getting around that. And one of the strategies, which I think is really cool, is that you can look at the two. We've got this here is this is the stator, the rotor out here. The Hallback array is actually the rotor. It's on the outside, and inside here is the stator. And they all have different magnetic cells you can think of going around there. And if you make them the same number of cells going around, that means as you're going around, you're going to keep on kind of locking in each little step. And what they've done rather cleverly is they've decided that for the Hallback arrays, they're going to use a prime number of these pole arrays that they put in there, of either like 7, 11, or 13 or 17 different ones along there. And the idea of having a prime number and making this like a normal integer here is there are no common divisors except the prime number itself. And that means the cogging happens more rarely as you go around there, as opposed to with very small steps of the motor. So that's like a a clever way of being able to improve it a little bit. And they go through here and describe a lot of the different designs they try to do to make sure that um, they come up with the optimized set of magnets and radii and the amount of material and everything in there to get the actual torque that they want to have. And then at some point, and more details here, exactly what they need to do also in the stator, how the windings are done in there. And so anyone that has a good degree in double E will probably understand a lot of it. But the main diagram, the one that I kind of focus a lot in here, is like, okay, how do they actually arrange these things to make the arm move? What's the arrangement that's going on here? And so this is what's typical in a lot of patents. It's a graphic they will put in there which reveals just enough information to receive the patent, but not too much information for anyone to really figure out what's going on. So you have to look behind the scenes here a bit to get an idea of try to imagine what's going on. Now there is a description and everything that's going on here, and I'm going to show a 3D mock-up of this. So the first thing I want everyone to see is like over here where my cursor is spinning around. This is where the shoulder is. And then here are two actuators. This is not a joint. These are actually actuators, a top actuator and a bottom actuator that using a tendon drive will actuate this particular joint over here. And this joint consists of 2 degrees of freedom, the one which is going vertical along here and the other one along here. Now it's kind of hard to understand in my description, which is why I'm going to build a 3D model to go along here. But the big thing is that where you think the joints are, or if you think there's a motor driving it at the joint, you were wrong. It's actually driving the next one. And we're going to see a lot of the advantages of being able to do something like that. So now what I want to do is I want to switch over to a 3D model, and I want to make sure. Okay. Yeah, let me just stop for a second here. Oh, I mean, I think I moved that. I'm going to bring the model up right now. Okay, so can you see
Yes.
that? Okay, so I took this in there to get an idea of what's going on. So again, if we look up here, I have this pair of red actuators, top and bottom, which are going to actually cause the motion over here on the shoulder joint. And what happens is that you can come along here and move this particular motor, and it's actually connected to what looks like this joint here. Now you see this green, what looks like an actuator moving there. Well, the actuator isn't actually moving. What's happening is the joint is moving at that point. Okay, it's causing the joint to move, and it's being done because of pretty much the tendons that go through a series of pulleys here to make that move. Now, depending upon the kind of movement you do, if you just move one of these motors, you'll get kind of a compound movement. And there's some other magic going in here that's not fully modeled, okay? But basically from the description, what is going on is that if you synchronize both of these red motors, the dark red at the top and the light one at the bottom, if they both move together, so you see that both of these are moving together, as they go around this spool here, it causes the arm to basically do a pitching movement. If I set it up that these two motors actually move counter to each other, so when one goes clockwise, the other goes counterclockwise, set it up right, what you will see is that when they go in the opposite direction, they are then going to basically cause this to roll. All right. So yeah, so the motor for actuating this joint is not here. Is here, it's not there. The green motor is actually what is used to actuate the elbow. So now I'm going to take the green motor here, and the top is going to move clockwise and then the other one counterclockwise. And you'll see what ends up happening is like you're expecting movement here, you're getting movement way down here. So you see when they go opposite, it causes the wrist to roll. And when they go synchronized together, it actually causes the elbow to move up and down. And so basically they have a split joint here where the tendon that's wrapped around the actuator up here comes down and gets wrapped around this. And if it only pulls on this one, only that one's going to rotate and you don't get the full rotation. It causes it to roll about this axis. But if both actuators are pulling together, that is how you get the pitching motion. So again, they both go together, and it's like, okay, these two tendons are pulling on there together. Now, to go the opposite direction, because you remember the problem with tendons, they only work in tension, they don't work in compression. You've got a second set on the other side that, you kind of look in there, you'd say, oh, there's some on the other side that are wrapped around the pulley the other way, so that when I go in the counter direction, I get the counter tension. And the way I'd like to describe that is like, anyone's had horseback riding, it's like you get the two reins in your hands, that if you tug on the right rein, the horse's head's going to move in one direction, but you kind of let the left one loose. And if you want the head to come the other direction, you pull on that and let the other one there. So it's not like you can push on one of the reins to make the head move. You need to have two to be able to go left and to go right. And that's the same thing. So just think about it. You pull on one side, you'll get it to rotate. And then if you get this split drum down here to go in opposite directions, and they have some other pulling mechanisms in here. So there's still a little bit more that's going on there that's able to take that motion and convert that rotational motion into a rotational motion along there. Okay, so you'll see that this is a very interesting kind of design. And if we take it one step further here, we now have the wrist down here. And in the wrist, the way we get the movement on the wrist is that the blue motors up here move. So if I move these synchronized together, I get the wrist pitching motion. And then if I switch it over to being opposite motion, clockwise and counterclockwise, you'll see what ends up happening is this very end here then rotates, which you can be used to get the yawing motion of your wrist. So it's done that way. Now, if you look at the wrist, you'll say, oh, there's motors here in the wrist. It's like, nope, there are no actuators here at the wrist. It's just this assembly here that converts the movement coming from the elbow. And again, the joint that forms the elbow is not the actuators. There's a separate joint in there for the elbow. And it turns out that's a convenient place to then put the wrist actuators down in there. So what does that mean? What this means is that we've been able to uncover a little bit of what they've been doing. So the original EveBot just had a very simple gripper, which was actually an off-the-shelf gripper from a company in Quebec called Robotique. And so there was like these parallel paddles that would be able to come down to grab things. So they went from there to coming up with the next generation bot, which we've seen they wanted to hide the IP here by blurring this thing out in the S3 documentary. So we don't really have a good idea of what's going on there. We can't see too closely. And like in one of the other images showing the hand, it's the same thing, because there's more than going on here than just the wrist. There's also a lot going on here with the fingers and the actuators that are in there. And that's like a completely other topic we can talk about after we talk about the tendon controls of the wrist. So that means they've come up with this hand, and this is a clip from their teaser where we can see a little bit of what that wrist joint looks like. So again, it kind of looks like what we're seeing in the patent. And I've annotated a little bit so you can understand this. Does that make sense?
Absolutely fascinating. Wow. I can see some cables also. This is cable. You remove it like white cables.
I think there might, we might be seeing something. It's hard to tell. So here we have what is this joint, the first green joint, which causes the pitching motion. And that's the axis of rotation along there. And then you'll see this other one that I highlighted in blue, which gives you the yawing back and forth. Now, the pitching motion of your hand is the most important movement. You want to go almost plus or minus 90 there. The yawing motion is not that important. Plus or minus 30, plus or minus 45 is all you need. And in some ways, if you look at the way this is set together, it seems like it's more favorable to do the green rotation than the blue rotation, which is fine. It's exactly what we want. We don't need to have a plus or minus 90 in the yaw. So if it looks like the hand's going to self-impact, if it moves too far, it's like, yeah, but that's okay, because we can't really move our hands back and forth that way that much. We can in the pitching direction. Now, if you look at the design of this wrist, this is kind of like a Cardan joint, or a type of universal joint where you have these two axes that intersect like that. And it's also a very similar kind of joint that you see in the Optimus wrist from Tesla. So right around here is where you have the pitching action, and you'll see that there's this servo drive here that has a very stiff rod. Instead of using a tendon here, Tesla is using a stiff linkage mechanism, which works both in tension and in compression. So this one actuator can push forward and backwards to make it pitch. Now, there's actually another actuator on the other side, and the two of them have to work together to make it pitch. And we can see down here where you have actually the two actuators next to each other. And if they move in different directions, that's what causes the yawing motion. Very similar to what we're seeing that 1X is doing. This idea that if you have both actuators moving together, things move in one direction. If you have them moving in a counter direction, then you get motion 90 degrees from the other. So it's a similar idea. But if you look at what Tesla wants to do, so remember the next hand that Tesla is talking about, they want to take all the actuators, which are fitting right here in the palm, and they want to move them back here to the forearm. Take a look at that forearm right now. How much room do you see in that forearm?
Not so much.
Not much. And basically the forearm ends right about there, because back here is the elbow and here is another actuator, which is to give you the rolling of the wrist. So this is like, we have 3 degrees of freedom of the wrist. 2 of them are actually out here, and one of them is sort of back here at the elbow. There's not a whole lot of room there, which means repackaging that is going to mean a lot of changes and a lot of differences. Either those actuators are going to be a lot smaller, or they're thinking of some other strategy. Now, the 22 DOF hand that Tesla is talking about is probably going to add yet one more actuator, because they have the abduction motion going on in the hand as well. And that means you have to throw one more actuator in there. So there's not a whole lot of room, which means that, 1X has already figured out how to do that.
Yeah.
Okay. Because they actually have one more degree of freedom. They're probably a 23 degree of freedom hand versus a 22 from Tesla, because they have one extra joint in the thumb. I shouldn't say they have one extra. Tesla has one less, because we actually have 3 knuckles. So this is more anatomically correct, the hand that 1X has here. And somehow they've managed in this very thin area to be able to fit the actuators they need for the hand. And then cleverly, by moving things back to the elbow, they don't have to worry about, well, where's the actuators going to be for the wrist? Oh, it just goes back a little bit further, and that's fine.
What we see here
very
in the blurred image, the colors, different color, like red, blue. What is
Oh,
this? These are. You can guess about it.
oh, I have no idea. I mean, I don't know if it's electronics in there or different color coding for cables or actuators.
It's very obvious. You
It's
use cables only. It seemed that they can fit all of that unless you
yes,
have cables. So.
yes. Now, the it's you've got at least 7 actuators in there, at least 7, and those actuators have to wind up these cables, which are going to be the tendons. Now, they only need to have like one direction, because basically everyone's hands, and we can even see it when we look closely here, is that they have torsion springs in the joints of all the knuckles. So when you release the tension, it's just going to pop open. So you don't need to have a second tendon to kind of pull it back the other way. And that's kind of how our hands basically work. We've got a lot of strength in clench, but not a whole lot for opening it up. So that's fine. So they just need to be able to kind of wind it up and release it. So they're either taking those tendons and winding it on, some little drum to bring it in the same way that you would do with a fishing line,
Yeah.
or they've got something that's just pulling on it. So, maybe they have like a really compact, and that's what I'm almost thinking, a set of compact linear drives that are about like a pencil, maybe very long, but very thin, that just is able to pull something in a distance of 1 or 2 inches, or 5 or 6 centimeters, something like that, because that's about all you need to get the fingers to go down. You don't need to have infinite amount of travel. You just need a short amount to get the fingers to close and to do that. So they could have a very interesting actuator design there. So I'm speculating here. I have no other information to be able to tell me they aren't, except that is a very, very sleek forearm that you're doing a lot of things with.
Very interesting. And I'm curious, where do you think this design could fail? Like if you think about like limitation that's in this design, can you guess it a little bit?
Okay.
Yeah.
I mean, part of it makes everything like the first thing everyone would point out is like, well, the tendons, those things are going to wear out. That's where everyone would be kind of worried about. And in the patent, they talk about using a synthetic type of woven fiber,
Mm,
most likely Vectran. And Vectran is very, very durable. I think it's even tougher than Kevlar. So if you pick the right material, it should work very well. So it's not going to be metal because the problem with using the metal tendons is they really don't wrap around spools very well. You end up getting a lot of metal fatigue over time. So you need to have a material which hopefully doesn't stretch. That's what everyone's going to say. Stretching is going to be a problem. This stuff doesn't stretch, and it rolls around these things really well and doesn't create a lot of friction. I mean, it is the ideal material almost for being able to do something like this. And of course, it's very, very light. So you can do that. And then the fact that you couple this with machine learning allows you to kind of adapt for everything that's going on, what's needed to be able to control your system. So in many ways, you might say, ooh, tendon drive is going to have all kinds of problems. The tendons are going to snap. They're going to stretch. They're going to lose calibration and do all this. I think they found a lot of ways of getting around that and are able to do things with pretty good accuracy. And again, the amount of power that they're consuming compared to the other bots out there is really a fraction. They're incredibly efficient. And we know they're efficient because you don't hear anything. When you're hearing the noises of actuators, what you're hearing is loss. You're hearing inefficiency.
mm,
And if you don't hear anything, that means all the energy is going into the movement like it's supposed to. Now, there's one other thing that's clever about this. So remember, we want to reduce the overall mass. And one way to reduce the overall mass is, of course, to make your actuators lighter and tighter, if you can do that. But the other thing is to find some way to be able to reduce the torque requirements of the motors in the first place. So I'm going to just use a simple example here.
sure.
Probably stop sharing to make it a little bit easier for us to be able to see that. And I think we're back up here somewhere here. And find everything that I've been sharing. Just bear with me here 1 second here. And somehow I managed to actually lose our screen. We're still here somewhere, right? Oh, there we are. Oh, okay. It was a different tab that's needed to be in. Okay. So I think we agree. Yeah. So what I'm going to do is okay. I'm going to put this in my hand. Okay. So I think we all agree that right now I'm able to move my hands. I'm able to lift a certain amount of mass and move my hands at a certain velocity, which is perfect. It's exactly what I need. But if now for some reason I decide to add mass to my hand or my wrist, we'll all agree I probably can't move my hand as fast as I used to. And I won't be able to lift as much because I now have to deal with this extra mass. Now, in order to overcome that, say I want to have the same properties, that I want to be able to go just as fast and still lift the same mass. I mean, I have to compensate for that by making the muscles in my elbow stronger. So I'm going to have to beef them up. I'm going to have to add more torque there. So I'm going to have to go out. And of course, doing that, I'm going to be adding more mass to these muscles, which means my shoulders are now going to be, because remember, the shoulders are having to also deal with this mass. So they're having to deal with this and the fact that now my elbow actuator is starting to get a little bit stronger. So from the standpoint of the shoulders, they're seeing this now. It's like I've added an additional mass onto the whole thing. So you see, you get this cascading effect that if you move all your actuators down to your wrist, which is what everyone else does. Tesla has done a fairly good job of moving it back, but it's still in the forearm. Everyone else, they basically says our joints are going to be our actuators. They're sitting out there and they're all having to carry that load, which means this has to carry that load. That has to carry load. Everything has to. And they talk about this in the patent, and it's a really good strategy. Their whole idea is the more you can move the masses closer to the torso, the lighter you can make everything. So that mass there is gone now, and you've put the actuator mass back here, which makes it a lot easier. And of course, the other thing we know is like, it's not just the mass, it's the moment of inertia, right? And the moments of inertia are usually what makes it very, very difficult. So they move that back. They keep on moving everything back. So if you need a stronger actuator, put the stronger actuator closer back there. And so they get the opposite effect. So rather than a vicious circle, they get a virtuous circle of the more we move it back, the lighter everything goes. So those are the two things. They made the actuators light to begin with and powerful enough. And then they don't need to be as strong because the placement of where they put it means the overall requirements on those things. They can even make them a little bit smaller. And so that's a lot of the genius and how they're able to get down to 30 kilograms and, be really energy efficient, not have to worry about, impact and problems like that. So it's really pretty clever. And I hope from that little demonstration,
I think
you're able to understand exactly how it
you did
works.
a great job on an investigation. I think it's really impressive. I'm just, yeah, I'm amazed how you managed to get. I think you actually cracked what they did already. They try to hide it as much as they can. Let you. It's business.
But there's still something going on the differential. So I mean, it's a very simple thing to kind of show that one of the things that they're doing as far as like I say, you don't necessarily need to have a motor. And I think I need to get the sharing back on here for a second here. That the that I'll do a little bit of a look in to what we have to get an idea of what's happening, and that is okay. So if we look in here, you this outer drum has a very high radius, let's say. So let's look in here. You see the this blue actuator. This is sort of where one of the tendons would come in and go around this spool right here.
Just the record.
Would wrap around that.
The blue actuator is linear one. The blue.
Yeah. So the blue one here is the one that's going to be making the wrist move. Yeah. So you'll see that right down here, and I should probably color these things different. But just imagine this tendon here is wrapped around this one with a lower diameter or lower radius, and then it comes out, and then it's now wrapped around here, just like a pulley, pulley system. That the fact that they have different diameters means they're going to have quote different gear ratios. So that we can see a little bit that I've put the gear ratio in there. That as I move this actuator, you'll see, and I just need to set it into the synchronization mode here, that as I move this one here, you'll see it has to move a lot in order to get the full movement here. So I put in a gear ratio of like 3-to-1, something like that. So it could be 3-to-1 or 2-to-1. So this might move for, when it moves 90 degrees, you only get 45 degrees of movement down here. So it's a little bit of a gear ratio, but it's not much. And the thing is as Bernd has said, is it allows you to get torque transparency. You actually understand what the forces and torques are that are being applied at that joint, so your control system can adapt properly to understand what's going on. But when you have a really high gear ratio, you end up losing that transparency and don't quite understand what it is that you have to do to control your system. So that's some of, again, the clever things that they've done. Now, what I've sort of shown here is that magically, when these things move in opposite directions, you get opposite movement out here. So if I'm moving this, you'll see the opposite movement here is causing this rotation there, or actually, I think it's easier to demonstrate it up here. So that when I'm moving the green ones in opposite directions, you'll see it's making this entire forearm rotate. And now you might kind of wonder, well, how exactly does it do that? Well, they've got something going on in here. There's a little bit more. There's probably some other tendons and a few other things that are converting this movement that as this kind of rolls along there, it's allowed to cause that movement to happen as well. So there's still a secret hidden well in there, which again is not quite revealed in the patent. It's discussed that they can do this and that with basically what looks like a word salad when you're reading it, trying to understand it. And and this part here is pretty obvious, but the other part not so much how they're doing it. And someday, I mean, everyone will find out. I'm sure someone will be, when eventually they actually get a robot, they will be able to disassemble it and take a look.
I appreciate the hard work you've been done there. Maybe the question I would...
that wasn't hard work. That was fun.
For you, it's fun, but for me, I'm impressed by your level of dedication and just to explain what is happening there, because they try to hide it as much as they can. But maybe the question I would like to ask you, since you interviewed the Figure CEO and all the other, so why they didn't do the same approach? Like, if we speak about Figure, like why they do the design differently? If is it something they like to understand, or it's not common to way of thinking how to design as much as 1X did? Like, where do you think where others like they didn't take the same approach?
Okay, so I think some of the approaches that are different. We know that, let's say most of the North American robot vendors have chosen to have these high gear ratios. Whereas the Chinese bots are going for these lower gear ratios, which is probably why they're able to get the walking a little bit better. Because again, it has a lot that has to do with torque transparency that makes it a lot easier for the control system to be able to adapt. And a lot of it comes down to the mentality of like we're trying to make these actuators as small and and as powerful as possible. And one way to do that is to get the mechanical advantage through having gear ratios in there. So that's, let's say, maybe not quite outside the box thinking. I think they all looked at tendons, and they are all using tendons at some point, in the hands. They already have to do that with the hands. The question is, where would they do it, more beyond that? The question is whether Tesla's going to be looking at that, because Elon has sort of intimated that, they're taking a lot of biomimicry of design. They're looking at how do the human body do the hand, and they're clearly redoing the forearm. But the question is, are they then going to be using different kind of drive mechanisms for everything else? Is the wrist, let's say, going to be tendon controlled now, as opposed to the actuators with these stiff linkages? That's hard to say. The thing is, tendons. There's still some other secret sauce that has to go on there, because is one thing that people could imagine is I'm not showing it in my rigid body analysis there, that as you start twisting these things, the tendons themselves are going to twist up. So it's nice when both spools are parallel, but when they start doing this, they start twisting in on each other. And when you start doing that, you start getting changes in length. And they discuss that in the patent, that's going to happen. And they have a way of being able to compensate that, which means you have to model it. So the modeling of it gets really, really tough to figure it out, because you're worried about what about flexion that's going on in the tendons, and they can only push one way, and then and you get this going around. So there's still a lot. And my overall feeling is if you were to do a tendon drive, especially if you were to make the tendon drives all in the torso, that everything comes right through here, with your puppet strings, that gets really difficult, because every single movement causes tension in another tendon that's going on. So what will happen, and this in a sense almost happens with our own hands, that is, if you try to move your wrist, you in effect are changing the tension on some of your tendons that could cause your fingers to move another way. And we kind of compensate. We mentally compensate for that, not realizing we have to do it. So every time you do that, you're changing something. And that's the other thing is we don't see in this design is we've only talked about how they've done the arm design. But now they suddenly have this hand, this 23 degree of freedom hand. Okay, I'll call it it's a 20 degree of freedom hand, not including the wrist. So all the movement they've got on there, they have to get tendons to go through that wrist joint. So we were looking a little bit at that wrist joint. What we're not seeing is how they're routing that cabling through, and how you kind of open that design up to allow that to happen. So they have literally a carpal tunnel in there somewhere to allow everything to come through to be able to do it, just like we have on our own hands. And again, that causes a problem. As that wrist joint moves around, the lengths of those things, the tensions on those is going to change. You got to compensate. And 10 years ago, I would have said, don't even do it. But now it's like, wow, with machine learning, maybe we just give enough data and eventually figure it out, because we're proof of the concept, right? That these kind of things work. And the reason it works is because of what's up here is able to compensate for all the weird flexibility and stuff that's going on down here.
This is really fascinating. I think we should do this every week. I think because there's many updates, so people would love to listen to you. And I think I'm really happy that you to learn about this in detail. But what do you think the next, like, if people look to what you mentioned, like, how do you see like Figure and other companies will think about their design? Because it seems that what we see now, the energy efficiency and this design. So do you think there'll be a shift in the design after what these?
Oh yeah. They all are. They all are. And we know it because they're all working on their next designs already. How much they're going to change and whether they're going to incorporate some of the things they see here, the learnings from other people, I expect they will. I mean, they're going to have to. And we already know Tesla's working on the Gen 3. That's finally out there. Barrett even said that Neo 2 is going to be fantastic.
When do you
So it's like,
do you have an idea? The Neo 2.
He says that they're already working on it. So they already have a concept. They're already doing it. That's something that he kind of dropped in the S3 interview, that it's there. And the fact that, he's the type of guy that he can never finish something. He says he gets like 95% complete and he needs other people to do it because he's on to the next thing. So he's already on Neo too,
Mm.
and that doesn't surprise me, And the same thing with Figure is they're already, the Figure 3 design is well along conceptually because Peter Diamandis let that cat out of the bag with his interview with Brett about 2 weeks ago. He said, the Figure 3 design I've seen is just absolutely awesome, and Brett just kept his mouth shut. He didn't want anyone to know
Do you have
about it.
an
It's like,
idea
that's
how it
there.
will look like the Figure 3?
No idea. So again, I think they'd be taking a lot of the learnings because they definitely changed Figure 2 a lot from Figure 1 and how to change the hip structure and everything else. So there's definitely a lot of changes. And I'm assuming that they're just looking at what's the next generation actuator is going to look like. So the thing is, you just can't keep designing, and you can always keep on coming up with a better design. And at some point, you have to commit and make some hardware and go out some testing and learn from that to figure out what the next generation has to do, as well as understand. It's like, remember, it's not, we're not just designing hardware here. We're also trying to take care of this embodiment problem, and we need to start getting data. And if we don't have the real bots out there collecting the data, then we're just pushing that date off when this thing is going to work. So we can sit here for the next 10 years designing the perfect robot, but if we're not actually collecting data and doing it, it's not going to help us out. So you see that that's the tension that they have between, do we wait for the next great design, or do we just go ahead with the best thing that we can kind of put together now and start conceptualizing how we're going to change it different.
Mm-hmm.
Now, I don't know how many are going to take the plunge to tendon control. It'll be interesting. I think everyone's going to kind of stay course with it, and it will really come down to what Tesla ends up doing. If Tesla starts going kind of in that direction as well, I mean, really changing everything. And this is kind of a prediction. I think I put it out there well, actually, I haven't quite put it out there. I've got a draft of kind of figuring out what's the state of the Gen 3 project right now. And it's not completed yet. So they said that it's still not design locked. They're still working on it and everything else. And that the hand is really just in the prototype phase, which means it's just, sitting on a workbench somewhere and everything else. They haven't got it all together, probably because they are really thinking everything through again. And they're probably trying to think about how do we change the hip and everything else, because the Gen 2 bot, I think they realized that there was a lot of design mistakes in there. And a lot of it, I think, was like the lower body. They're just not getting the speed, the walking speed out of it. So it's a really strong bot. It could probably deadlift a lot if it has to. It just can't walk very fast. And you really want to be able to walk fast. And some of it is that they may have like the wrong types of actuators. Maybe they shouldn't be using linear actuators. They should just use rotaries like everyone else. So they're rethinking everything top to bottom. And the question is, if they're rethinking everything top to bottom, whether they're really going to think outside the box. It's like, okay, how does nature actuate the shoulder? It doesn't have 3 motors in there. The robot joints, I've mentioned this many, many times, everyone has, is not even close to what the human joint is. And the human joint is a simple ball and socket joint. And why doesn't anyone do that? Why don't we just have a ball and socket joint in our humanoid bots? And the reason is because it's so difficult to actuate a ball and socket joint.
You said this before.
The only way you can, and the only way you can really do it is with, basically different kinds of tendon controls and everything else. So let's see if that happens. And when that happens, then suddenly everyone else is going to break. The only other company out there that is really going down that whole idea of, let's say, not quite tendon control, but looking at inspiration from it, is Clone Robotics. But they're really in Poland, but they're really a research project that's doing a lot. They haven't been able to put something together, but it's a very interesting
And it's
novel
bulky.
approach.
It's very bulky. I mean, they're actuators. They have a lot in them. I think what's interesting about when they actually compact everything in a very small area.
Yes. That's what they managed to do. And this is the other thing, is that I did put a post out there, saying that the 1X hand is clearly the best hand out there. Mm-hmm. And it's probably even better than the 22-degree frame hand that Tesla has not shown yet, that in the design phase. Now, there are some good hands out there, but there's some limitations on some of those hands. And some of the hands that are really good, they're not on a full humanoid body or bipedal bot. So it's like, okay, you can have this hand that can do the Rubik's Cube thing, but I'm not seeing it actually mounted on a humanoid bot. There must be a reason. So if you look at it, it's an incredible hand, the best hand that is actually integrated into a fully bipedal humanoid bot. And how they've been able to do that is just amazing. I mean, it's a big problem. You can come up with a great hand. You'll see it in Hollywood. They'll have some of these, incredible hands that they use that they have in some of these movie scenes. But then, it's like behind the box, they got to have all this other stuff to be able to do. And it's really hard to miniaturize that stuff to be able to fit it into an arm that's going to be attached to a humanoid bot that's walking around. So the fact they were able to pull it off in one generation is amazing.
Yep.
And then the fact that they didn't say, oh, we'll take the shortcut and, get rid of the knuckles and make every finger the same length and do this and that. It's like, nope, it is a true human hand.
Few question. Do you have an idea for Burnett how the time duration where they come up with the design? Because they have Eve. I'm not sure the timeline for the research and production. Do you have any anticipation about the timeline they came up with?
Yes. Well, it seems that, so he started in 2015, and they were really looking at the actuator design and everything else and got that moving ahead and got a patent also out there for being able to reduce the cogging problems that they have in there. So there's also another patent regarding that. And then the idea of these actuators. So that was around 2020, and definitely they were looking at Eve, and then also trying to figure out, well, how do we actually get the training data? What should our bots look like in picking up that? I think now they're going to be every 1 to 2 years, probably new design. I mean, if they've already got another one for Neo, we'd probably see something, I imagine, within a year to 18 months. And this seems to be the iteration cycle you see in a lot of companies. Sanctuary has done the same. I think they're on their 7th generation now. They've been around since 2018. Tesla is getting ready to work on their 3rd one. And Elon even said that, the Gen 3 bot is the one that's probably going to be going into production, that they'll be going everywhere, about 1,000 next year. And then within 5 to 6 years, it would be about 1 million. So if they're starting from a base of 1,000, which they probably could do next year, that means they're only planning and scaling about 3x per year to get up to that. And he said that in that time period, he expects 2 to 3 major revisions on that bot itself. And it just comes from the fact that, his overall feeling is that every product, it's usually the 3rd generation of the product when everyone finally gets it right. And everyone say, yeah, the iPhone 1, it was like kind of interesting, but it was really like the iPhone 3 when it came out that people said, okay, I'm ready to buy this thing. The same thing with the Tesla Model 3 and stuff like that. Yeah, you waited a little bit for them to get some of the bugs out of the system, a little bit of changes. And it'll be the same thing with the bot. Not to mean that the Gen 3 bot won't be good. It will probably be pretty good and pretty amazing. And then they will learn a lot from that. So it's not really their first bot, even though it might be the first thing people can buy. They really have gone through 3, you can almost say 4 generations, because they had Bumblebee before that. And, same thing with 1X and everyone else, is that they're going to be iterating. So I expect every 12 to 18 months, they will always announce a new model.
Yeah, one question also about the cost, because what 1X did, like reducing the cost and making it efficient. How do you see the cost-wise being useful? You said that the useful thing that the robot can do and the bot can do, but the cost also element, because I think if 1X, I'm not sure the competition between the prices and it will be significant, the cost of these things.
Yeah, a lot of it is if you're very light, that's, if you have half the material, that brings a lot of your cost down already, because at least your raw material cost goes down. But the raw material cost is usually small compared to the actual taking those things and forming them into the right combination of atoms that you need for all of it. So if you look like, I think I did this calculation with Optimus, you say, oh, if it's all made out of aluminum, Optimus would only cost $140. That's the spot. If it was made out of titanium, all titanium, then it would cost $8,000. So yeah, you want to be careful what you buy. And it has a mix of copper and some other things in there that will add a little bit to the cost. But a lot of it is the manufacturing, the assembly, and everything else. And a lot of companies, including Tesla, said, well, the way to bring the cost down is make the hand design as simple as possible. Remember, all the fingers the same length, only 2 knuckles on there, and try to use the same actuators designed in many places. So even though they have 42 actuators, there aren't 42 different actuators. There's only like 7 different types of actuators, and you just kind of stack them up in a particular way. And 1X has sort of done the same thing, is to make sure that they don't have too many families of actuators, that they're just focusing on one type of rotary actuator, do everything with the tendon drives. That hand, I look at the hand and think, wow, that's probably going to be the most costly part, because it's so specialized. Each knuckle is unique and a little bit different. So I'm not sure how many components they can reuse, but they may be confident that it's like, look, if we can make this little distal joint here, for low cost, we can make this one and this one. All the others are low cost. It's just a question of, kind of assembling them together. So they seem to be pretty confident that they can get the price down there. And I don't see why not. This is something that I have observed before, and it's been brought up a couple times. And it was interesting to hear Brett also bring it up, in that there was a time when Tesla was not good at manufacturing. They didn't know it. They had to learn it. So right now they keep on saying, oh, it's like they're so good at manufacturing. There's this moat. And it's like, that's true. That's an advantage, current advantage to have over everything. But it doesn't mean other people can't also, be clever and good at being able to do manufacturing. They're going to learn. It's going to take them a little time and effort to do it. But they're not trying to assemble a Cybertruck or Model 3 or something like that. They're actually assembling something that is a lot easier, a lot simpler to do. So that means, they can also get the manufacturing prowess together when they need to at some point.
Person. Maybe the final question about the leg. Since we see now what happening in the hand of 1X, how do you see that the leg will be that future iteration? Do you think there's something like this, like thinking outside the box to make the leg movement? Yeah, we see that Optimus a little bit. They have the linear actuator, but yeah.
Yep. But I think the the 1X is basically using the same combination. So your arms and legs are basically very much the same thing. Their morphology is a little bit different, but for the most, all intents and purposes, it's the same thing. You've got a ball and socket joint here for your shoulder. You have one down there in the hip, just sort of different size actuators. So they're probably taking almost the exact same approach. I mean, your knee and your elbow, they're almost the same. And your foot is much simpler than the hand. You don't need to have full degrees of freedom in your wrist. So we have a 3-degree of freedom wrist, but our ankle is really 2 degrees of freedom. There's kind of a third one in there, but you really don't want to do that. It usually results in an injury. So that means the arm is 7 degrees of freedom, because we have redundancy from the shoulder that causes a redundant elbow. But legs are always 6 degrees of freedom. So it's actually a little bit easier for them. It's just a question of the size that they need to make the actuators. But because they're only toting around 30 kilograms, it'll make it a lot easier. And Barrett is confident. They run the numbers, and I'm pretty sure they're not showing it yet, but I'm pretty confident by the end of the year we will see what he really said, that can walk 2.5 miles per hour,
Wow.
which is exactly what you want, and run at like 7. So it will actually be able to go into running gait, running and jumping. So it's like, well, okay. Can't wait to see it. And I'm pretty sure they'll be able to do it.
Awesome. Thank you. Thank you, Scott. It was really fascinating, as always. And I appreciate the hard work. I know it's fun for you, but it was really, for me and others, it's just to appreciate sharing this knowledge with us. So I appreciate it.
Yeah. Well, I'd love to share. So thank you for the opportunity to actually go ahead and share this with everyone, because, sometimes you learn these things, you just want to tell everyone about it. So.
Thank you.